In this section, we will introduce some best practices for shader programs to help you get the best performance on Mali GPUs. Fine-tuning shader programs is often one of the first things that developers ask about optimizing. But we'd recommend starting to optimize content, data flow, and API usage first, as they are easier and usually give larger gains. The major recommendation for shader programs is to use medium P or Vulkan relaxed precision wherever possible. This maps to 16-bit, half-float, and integer types. These are more energy efficient, use less register storage, and can execute faster as the Mali hardware supports issuing vector-2 pairs of 16-bit operations at the same speed as a single 32-bit operation. There are some cases where 16-bit types lack the dynamic range and precision required. In general, 32-bit high-P variables are needed when computing positions and distances in world space, including for depth-related computations such as shadow mapping. We would also recommend using 32-bit interpolants for textural coordinates, although the input coordinates for each vertex can be stored at 16-bit in memory. For most textures, only the interpolant needs the additional precision. Developers usually overestimate what a shader compiler is able to optimize on their behalf, especially for floating-point arithmetic. In this example, we can see two texture samples being scaled by the same scaling factor and then added together. In real-world mathematics, it's a valid rearrangement to add the two texture samples first and then scale the results second. This saves one vector multiply, so looks like a great optimization. However, with floating point, this is not necessarily a safe change for the compiler to make. For the rearrangement to be safe, we are asserting that the two equations here are equivalent. Let's plug in some numbers and see what happens. For the purpose of this example, we are setting A and B to the maximum value of a half float and scaling by a half. On the left-hand side, we see the original arrangement. We scale each value down by half, and then add them together to get back the expected answer. On the right-hand side, we see the optimized version. We add A and B together, but this overflows the maximum capacity of a half float and gets turned into an infinity. When we come to scale this back down again, infinity times a half is still an infinity. When using floating point operations, these two expressions are not equivalent. This issue with reassociation means that shader compilers are very cautious at rearranging shader code, even though on paper, we are allowed to reassociate. Without knowing the values of the variables involved, it's very hard to tell if a rearrangement will introduce an infinity or cause an unacceptable precision loss, resulting in unexpected rendering artifacts. The solution to this is for the shader authors to be the compiler, and optimize the source as much as possible based on their knowledge of what is going on. Shader languages have a large library of built-in functions and vector manipulation operations. It is nearly always more efficient to use these built-in functions than it is to roll your own implementation. They are either backed by hardware or some hand-tuned library functions for that specific GPU version in that device. Here, we see an example implementing a video color key, discarding fragments that are between two color limits. Not only is the built-in version faster to execute, it's also a lot easier to read. Built-in function runtime also depends on variable precision. Medium P versions are usually faster than high P versions, so try to keep precision down where possible. Some built-in functions are relatively expensive, so we recommend not making heavy use of them. These include trigonometry functions such as sine, cosine, atomics, and the texturegrad function. Shaders often contain uniform computation, meaning computation that only depends on literals and uniforms. This computation will produce the same answer for every thread in the draw call or compute dispatch, so it's best moved out of the shader code and on the CPU as something executed at draw time. It is worth noting that the Mali drivers will optimize this away to some extent. We really don't want to repeat the same calculations for a million threads, but there is still some overhead and it cannot be optimized away completely by the driver. We recommend specializing shaders for particular usage patterns, compiling specific program variants for the most common usage in the game, rather than having single uber shaders with complex control or data flow. Specializing control flow for if-else conditions avoids every vertex or fragment repeating the same condition check and branch operation. Embedding loop limits as literals, rather than uniforms, gives the compiler compile-time knowledge of the control flow, allowing precise loop unrolling. Specializing data values, converting values that never change from uniforms to literal constants in the source code, gives the compiler more latitude to optimize expressions and pack simple constants into instructions at compile time. Some aspects of specialization are tied to the draw call type used. Uniforms that are stored in an array and accessed in a dynamic index, such as GL instanced ID, are less efficient to access than flat uniforms. We therefore recommend avoiding using instance draw calls when only a single instance is being drawn. This is another one of those areas where there is this balance to find between the benefit of specialization and the overheads of creating and managing a large number of shader variants. There isn't any right answer, and developers need to find a balance that works for their application. This advice is less important than it used to be, but there's still a large number of Midgard architecture devices in the hands of users. Utgard and Midgard GPUs have a SIMD instruction set, so the compiler needs vector operations to pack out those functional units. It will auto-vectorize if it needs to, but it's always better if you use the vector types in the language. There is a huge amount of misinformation online about the role of branches in GPUs, and whether they are good or bad. On older SIMD-based GPU instruction sets, branches are expensive. This is not because of the branch itself, but because the use of branches breaks up the program into smaller basic blocks, which gives the compiler less scope for packing SIMD instructions with useful work. On modern scalar GPU instruction sets, branches are relatively cheap. Not free, there is still some condition logic and a branch instruction to run, but definitely not expensive. The one caveat to this is to be aware of control flow divergence across a warp. Modern hardware runs with multiple threads in lockstep, and if some of the threads in a warp take an if, and some take an else, the hardware will run with lanes masked out, which can rapidly erode efficiency. Here, we can see an old-school specular light shader, accumulating the light contribution from 3 light sources. This shader tried to be clever, skipping the light calculation for light sources which are too far from the current fragment. For a Mali T860 GPU, which has a SIMD instruction set, this shader has a 5-cycle cost if all lights are skipped, and a 13-cycle cost if no lights are skipped. We can optimize the shader by removing the distance check and branch, always executing the lighting calculation. In this case, we can see the shortest path gets slower, increasing from 5 cycles to 7. But if all our lights are active, we've almost doubled the performance of the shader program, reducing from 13 cycles to 7. Hopefully the application isn't rendering many objects where all the light sources are cold, so this is a significant gain. For these older SIMD-based GPUs, just performing a computation is often less expensive than attempting to skip around it with control flow. While branches can be expensive, don't go crazy trying to avoid them. Graphics compilers are very good at replacing small branches with arithmetic-based alternatives or conditional selects. If you are not too sure, use a tool such as the Mali offline compiler to check if your shader really has a problem that needs solving. Mali has a vector-based load store unit and interpolator, so it is always best to try to load full vectors to make the best use of the available hardware width. For example, in vertex shaders, loading a single vector 4 attribute will be more efficient than loading 2 separately bound vector 2s. In fragment shaders, interpolating a single vector 4 will be more efficient than interpolating a vector 3 and a scalar. Ideally, applications remove as much redundant overdraw as possible, using early ZS testing or hidden surface removal. Some shader functionality will disable some of these optimizations as state is not known until the shader is executed. Using discard statements, commonly for killing alpha-tested fragments, allows for early ZS testing, but disables early ZS update and hidden surface removal. Using a programmatic depth write disables all early ZS and hidden surface removal. Using a programmatic depth read from the frame buffer allows for early ZS testing, but disables early ZS update and hidden surface removal. Using a programmatic color read from the frame buffer or from a pixel local storage structure disables hidden surface removal. For content doing late ZS operations such as these, it is often possible to disable depth testing or mask depth writes if the updates are not needed. These can help performance. It is also possible to add layout, early fragment tests, in the shader, which inform the compiler that it is safe to use early testing, even if the shader uses one of the operations above. Finally, we get to tuning compute shaders. The first thing to choose is the workgroup size for your target device. This can have an algorithmic impact, so it needs some consideration. But from the GPU point of view, we want workgroups that are not too big and not too small. We would suggest starting with a workgroup size of 64, but whatever you choose, make sure it's a multiple of the warp size of your target hardware. It's worth noting the optimal workgroup size can vary from GPU to GPU, so it can be worth running some tuning benchmarks when your games first run to select the appropriate size for that specific device. The Compute APIs have the notion of a workgroup shared memory, a pool of memory that allows threads inside a workgroup to exchange data while the workgroup is running. On some GPU hardware, this is a dedicated RAM, which is faster than main memory, so applications copy data from main memory into this dedicated RAM to gain performance. This is not true for Mali GPUs. Workgroup shared memory is simply a buffer backed by system RAM, so copying read-only data from global memory to workgroup local memory will actually make things slower as you are just polluting your cache. Use workgroup local memory only for algorithmic data sharing. This concludes Module 2 of the Mali GPU training. You now have a wealth of knowledge about how to build efficient, performant apps. In the next module, we'll show you how to use our Mobile Studio tools to identify some of the common problems we've highlighted here.